Alright guys, so today we're going to be talking about how to find the pH and the pOH of acids and bases. So really, what is the pH and what is the pOH? And we're going to start off this video by understanding a couple prerequisite concepts when it comes to finding things like concentration of H plus and concentration of OH minus ions, and also finding the pH and pOH of acids and bases. So representing in this green line, we have pretty much a rough drawing of the pH scale. The pH scale runs from 0 to 14. 0 being really, really acidic, like hydrochloric acid, which can be found in our stomachs, or 14 being really, really basic, like sodium hydroxide. And right in the middle, which is 7, is neutral, like pure water. And a couple things that we have to know before we solve problems dealing with this concept is that the pOH plus the pH will equal 14. And that makes a lot of sense because that essentially means that the concentrations of the hydroxides and the pH, the H plus concentrations and the pOH and pH of those have to equal the whole pH scale. You can find the pH individually by doing the negative log of the H plus concentration, which is represented by the bracket H plus. Same thing with pOH, but you're going to use the OH minus concentrations. And also, a very, very important concept when it comes to finding pH and pOH is this water constant. Water constants are very important when it comes to finding things like H plus or OH minus concentrations. Now, the constant, the equilibrium constant for water, which is represented by this Kw, is 1.0 times 10 to the power of negative 14. And this is very important because it was founded that the concentration of H plus times the concentration of OH minus equals the equilibrium constant for water. So we can manipulate this equation to find individual concentrations, which you'll see pretty soon. Now, the thing in green, these two asterisks in green are very, very important because they kind of give you some pre-assumptions that you have to make when it comes to solving these problems. The first assumption you have to make is that the temperature is 25 degrees Celsius. That's the most normal temperature that we'll use when it comes to dealing with acids and bases. And if we use a temperature above 25 degrees or below 25 degrees, our Kw value will be affected. Like if our temperature increases, our Kw value will actually increase and vice versa. So because we want to keep our equilibrium constant for water the same, we're only going to assume that the temperature is 25 degrees Celsius. Also, H plus and hydronium, H3O plus, are essentially asking for the same thing. So if they ask you for the concentration of H plus or they ask you for the concentration of hydronium or H3O plus, they're pretty much asking for the same thing. All right, so let's get a couple problems in here to get a better understanding of how we can apply this knowledge into some problems. So let's say, I'll get rid of this. Let's say that we had some solution and its hydroxide concentration is 6.8 times 10 to the negative fifth, 6.8 times 10 to the negative fifth moles per liter. And we're asked to find whether the solution is acidic, basic, or neutral. So is it a acid? Is it a base? And I'll do it in a different color. Is it acidic? Oh, this is still green. Is it acidic, basic, or neutral? And B, calculate the hydronium concentration or the H plus concentration, or because they ask for hydronium, we'll say hydronium here. Calculate the hydronium concentration. So how do we go about this? Well, we're given our OH minus concentration. So what can we find with this information? Well, we can find our H plus concentration and we can find our pOH. Now, what's actually important for this problem? What's important for this problem would be finding our H plus concentration first, because that can answer our part B. And how can we do that? Well, we can use this equation. The concentration of H plus times the concentration of OH minus equals the equilibrium constant for water. So if we use that equation, H plus concentration times the concentration of OH minus equals the equilibrium constant of water, we can see that, okay, we're trying to find our concentration of H plus, and we have our concentration of OH minus, which is 6.8 times 10 to the power of negative 5. And that equals our equilibrium constant for our water, which is 1.0 times 10 to the negative 14th. So if we divided both sides by 6.8 times 10 to the negative 5, we would get that our H plus concentration would be the following. It would be 1.5 times 10 to the power of negative 10 moles per liter of H plus. So what can we do with this information? Well, with this information, we already solved part B. We already solved that our H plus concentration, and remember, based off of this assumption, H plus and hydronium are essentially the same thing. So if this amount of H plus is there, the same amount of hydronium will be there. So, and I guess because the question asks for hydronium, we can rewrite our H plus as H3O plus. So because we've solved for part B already, solving for part A has become very easy, because now we have to find the pH and compare it to this scale. All right, so I guess I will erase a little bit of this top equation here, and I'll use this equation, our pH equation. Well, we know that pH is equal to the negative log of our H plus, or our hydronium concentration. So if we do our pH equals the negative log of our H plus, our hydronium concentration, which we found out to be 1.5 times 10 to the negative 10 moles per liter. So if we type that in, 1.5 times 10 to the power of negative 10 moles per liter, we would get that our pH is in fact 9.82. All right, our pH is 9.82. So we're given a pH like this and a hydronium concentration of this. So how do we know if it's acidic, basic, or neutral? Well, a rule of thumb is just remember your pH scale. If it's 6 or below, it's acidic. If it's 8 and above, it's basic. And if it's right in the middle, 7, it's neutral. So here we see that we have a number 9.82, which is greater than 8. So we know that our solution is going to be basic. So let's try another problem. Let me erase this. All right. And this one is a multi-part question just like the first one. And it asks us the pH of some solution, is equal to 5.53. So we know that it's slightly acidic. We know that it's on the acidic side. It's lower than 6. And the question's asking for the H plus concentration. So that's the part 1 of the question. The OH minus concentration, part 2 of the question. The pOH of the solution. And it also asks us if it's acidic, basic, or neutral. All right, so we can already sort of agree that that the solution is going to be slightly acidic, mainly because we know that if it has a pH of 5.53, that number is below 6, so we know that it's going to be acidic. Now, regarding the part of the question asking for the concentrations of H plus and OH minus and pOH, we have to use this information once again and these equations to solve the problem. So we have pH equals 5.53. What are some immediate things we can find from this information that will help us find the rest of this? Well, we can immediately find our H plus concentration by using, once again, this equation. We can use pH is equal to negative log times the concentration of H plus. And since we know that the pH is 5.53, we know that we can take the negative log of something that we're not sure of, and we can solve for H plus. The way that we can solve for H plus is because we know that if there's a log and there's a concentration, it's with a base of 10. So we can take 10 to the negative 5.53. Because of the negative log here, we have to take 10 to the negative 5.53. So 10 to the negative 5.53. Type that into our calculator and get the answer 3.0 times 10 to the power of negative 6 moles per liter of H plus. So we solved for our H plus concentration using the pH equals negative log times our concentration of H plus. And by taking the base of 10 to the negative 5.53 power, because we know that it's the base to some power equals something. So the base to some power to the negative of that power, because it's a negative log, will equal something. And that something is 3.0 times 10 to the power of negative 6 moles per liter of hydrogen, or of H plus. So using this information, we can find our OH concentration. How can we do that? Well, and let me make some space here by quickly erasing. We can do that by using this equation. If we know that our H plus concentration times our OH minus concentration is equal to our equilibrium constant of water, we can tell that from the information we found before, the H plus concentration, which I said was 3.0 times 10 to the power of negative 6 moles per liter, and we want to find our OH minus concentration, we can set that equal to 1.0 times 10 to the negative 14th, which is equal to our kW value. And if we divide both sides by 3.0 times 10 to the power of negative 6, then we can find our OH concentration to be 3.3 times 10 to the power of negative 9. And sorry, this negative is supposed to be on the inside. I'll scratch that. And this will be our OH concentration, moles per liter of OH minus. All right, so we solved for our OH minus. And how do we solve for our pOH? Well, we use this equation. We take the negative log of our OH minus, which of the concentration of our OH minus, which is 3.3 times 10 to the power of negative 9 moles per liter. And it has to equal our pOH. And if we type it into our calculator, we would get that our pOH is equal to approximately 8.47. Thank you for watching this video. There might be a part 2 segment further explaining some more difficult problems dealing with strong acids and strong bases, but I hope that this gives you a solid foundation on how we used all of these equations to solve for some basic problems dealing with finding the molarities of H plus and OH minus, and also finding the pH and pOH.